So to talk a little bit about the species of interest, we're talking about Metacosmus magister, which was previously known as Cancer magister and commonly known as the Dungeness crab. It's a keystone species along the U.S. West Coast as it provides essential food web links for many marine animals as well as terrestrial. It funds local coastal economies and fisheries across the West Coast and is considered a very successful fishery. And it also is an indicator species as vulnerable to environmental stressors related to climate. And as climate variability increases with climate change, it's also increasing in other environmental factors. One of the lesser studied components is the ENSO cycle. And this is El Nino Southern Oscillation. It's a major climate driver that consists of the shifts between La Nina and El Nino phases. And basically, in simpler terms, it's kind of cold and warm years. So the goal of the study is to find if there's any correlation between the ENSO variability and Dungeness crab populations by doing some biophysical coupling. And to get to that goal, I have 3 objectives. The first one was to characterize biological patterns of Dungeness crab through horizontal, vertical, and temporal distribution. So we're going to look at the depths and the latitude and longitudes. And then we wanted to quantify the variability in ENSO cycles through amplitude and periodicity. And then finally, we wanted to do some biophysical coupling between the two by investigating the coherence and correlation between observed biological patterns of Dungeness crab with the ENSO cycle amplitude and periodicity. So this study took place on the U.S. West Coast, and we used RStudio for all of our analytics. We used 2 data sets, one of which was for the environmental data, the ENSO multivariate index, or MEI. This is basically one value that encompasses all of ENSO, so we know whether we're in El Nino or La Nina phase. And it's calculated from multiple environmental variables, such as surface wind stress, sea surface temperature, surface air temperature, sea level pressure, and total cloudiness fraction of the sky. And we categorized normal ENSO phases as an MEI value of plus or minus 0.5 degrees, and an extreme ENSO phase as an MEI value of plus or minus 1.5 degrees. And then for the biological data, we took from the West Coast Groundfish Bottom Fault Survey, and unlike its name, it's actually an overall ecosystem survey, so it also takes invertebrate data. And this uses a stratified random sampling technique, which I'd like to add is a little bit of a unique method for analyzing crab populations, as usually we're using catch data from commercial fishermen. So this shows us a different look at the population from a non-fishery-dependent data source. We're using the catch per unit effort from 1975 to 2024, along with the latitude, longitude, and depth information. And the equipment used for collection is commercial fishing vessels equipped with scientific trawl gear, like the one figure with the boat that's showing an Aberdeen trawl, which is the standard netting used for this survey, and as well as sensors to ensure data quality and consistency. And the top picture is just of one of their fleet boats after it's dragged off the bottom and brought up the sample, and that's just the data or the specimen separation and collection. So for the first objective, we wanted to characterize the biological patterns. So this shows the yearly horizontal shifts divided into individual decades of Dungeness crab catch per unit effort centroids. So it's showing the yearly centroid of catch per unit effort. As you can see from the first decade in the top left, there's limited spatial coverage, and that's due to this being the start of this survey. So there was kind of some limited data there. But if you look in more recent decades, such as 2006 to 2015 and 2016 to 2024, you can see that the catch per unit effort is increasing in the recent decades, as well as the spatial variation of the centroid shifts. They're decreasing in recent decades. So you can see that the latitude range is from around 41 to 45 degrees, but in the last 2 decades, it's consistently been within 42 to 44 degrees, so that's a 2-degree decrease of centroid. This is the vertical distribution of Dungeness crab. So this graph is showing the relationship between depth and catch per unit effort. The light blue points are just showing the overall depth distribution. So you can see that the majority of the population is within the 200 meters, from 50 to 200 meters roughly. And the dark blue line is a cumulative distribution function, or a CDF. And that's basically just telling us the percent of total catch per unit effort accumulating as the depth is increasing. So roughly 90% of the population is found at 200 meters or less, and then the last 10% or so can be found distributed all the way up to 830 meters. Next, this is the environmental patterns from Objective 2. This is the multivariate ENSO index monthly values. So this runs on a decadal scale of 2 to 7 years, and I marked a few different things in this graph. The horizontal dashed lines are depicting the normal El Nino and La Nina thresholds, and then the red and blue vertical lines are showing significant La Nina or El Nino events, and the green vertical lines are showing regime shifts, and these were all taken using NOAA climate data. So finally, for Objective 3, we wanted to do a biophysical coupling between the environmental and the biological data. So this is ENSO's influence on the horizontal distribution. This graph right here is showing the latitude and longitude's deviation from the mean position, green being longitude and blue being the latitude. And below that, we just have the yearly MEI values. And with the Pearson's correlation coefficient, we calculated that there was a weak positive correlation between ENSO and the latitude deviation. So as ENSO's increasing, the latitude deviation is also slightly increasing. But the p-value showed that there's a lack of statistical significance in this. And similarly, we calculated a weak negative correlation between ENSO and the longitude deviation. So as ENSO's increasing, the latitude deviation is decreasing slightly, and this is not statistically significant. Next, we performed coherence between the two. We found a mean coherence of around 0.87, which suggests that there's strongly correlated variation between ENSO and Dungeness crab horizontal distribution. We found a peak coherence at about 5.2 years, and this aligns with the typical ENSO cycle period of 2 to 7 years. We found the p-value is also greater than 0.05, so this is also not statistically significant. Finally, we have some wavelet analysis. So to explain this a little bit, on the y-axis we have period and log scale. So we have roughly 16 years at the bottom and 0 years at the top. And then a time scale in years on the x-axis. And anything that's surrounded or surrounded in black lines shows statistical significance. The gray shading is the cone of influence, which indicates less reliable data due to an edge effect when you're inputting a wavelet into R. And then the red coloring indicates high coherence, while the blue indicates little to no coherence. And so we found coherence on a long-term scale and a short-term scale. So the short-term coherence was about 3.2 years. It's on the top right. It's more so occurring in recent decades, and there's little black arrows within the area of significance. Those are lag arrows, and they're pointing down and to the right. This indicates that ENSO influences catch per unit effort positively, so they're in phase with a time lag, and then the long-term coherence of about 15.5 years, the lag arrows are going upward and to the left, which indicates that ENSO influences catch per unit effort negatively or out of phase with a time lag. And this implies that ENSO influences Dungeness crab catch per unit effort at multiple scales. And then I did a wavelet coherence with the average squared coherence. This is basically visualizing the overall strength of the ENSO to catch per unit effort coherence at those different flagged times that we just looked at. So at the 15.5-year period, the coherence was high at 0.9, and it was statistically significant. So this shows a really strong signal. It was also statistically significant at the 12.5-year period and the 3.2-year period, which was the one within the ENSO 2 to 7-year band. So what this all means, in summary, we see variability in ENSO is affecting the temporal catch per unit effort and the horizontal distribution of Dungeness crab. On the short-term scale of 3.2 years, the coherence is within the ENSO cycle range. The long-term coherence of 15.5 years might suggest that there's a larger climate regime impact at play. And for the horizontal shifts, they exhibited strong alignment with the ENSO cycle. However, there was no statistical significance, so it would be hard to show a significance relationship. And so what this means for management, I think it's important to consider the ENSO cycle trends when you're setting quotas and setting harvest location restrictions. Monitoring the ENSO cycle phases and strengths could potentially offer improvements for seasonal and decadal fishery harvests and forecasts. And the implementation of an adaptive management strategy like this might be needed during especially extreme ENSO events or as variability increases in the future with climate change. And so in conclusion, climate and ENSO-informed management could contribute positively to the resilience and sustainability of the Dungeness crab fishery. Thanks. Any questions?
You answered them all.